Let's go ahead and get started. I want to give a shout out to people in the room and everybody on Zoom. Thanks so much for joining. Really excited to give this workshop today. From p-values to predictions. Yeah, so my name is Scott Comulada. I have a faculty appointment at UCLA. And before I go further, I want to give a big acknowledgement and shout out to the team. I think most of them are here on Zoom. So in case you don't know, I'm part of a scientific working group through the CFAR, that's between UCLA and Charles Drew. And the CFAR is funding this scientific group that's focused on AI methods and HIV research. And we really want to, through workshops just like this, we want to enable HIV researchers to be able to use AI and machine learning tools. So this is one workshop. We've had some great seminars already, and we will continue to have seminars. If you are not on our listserv, we have your email today, but just in case, if you also want to make sure you're on the listserv, please feel free to email Johnny, who was the person who sent out the invitation. So what am I hoping that you're going to get out of this workshop today? This is a workshop focused on AI and machine learning methods. So what I really want you to get out of it is a better understanding of when you would use AI and machine learning methods versus traditional statistical approaches. Understand the modeling issues, because there certainly are some unique modeling issues when you use AI and machine learning. And then I'm also going to show some Python code and run through the basics of setting up a data set, a pipeline, selecting a model, and evaluating it. Now, I know some of you might say, I don't want to learn Python, and you don't have to. So even if you don't want to, you're still going to get something out of the workshop today, because I'm going to cover very general issues, but I am going to present Python code. So I know this morning that Johnny sent out files for the workshop, so you can actually reproduce everything I'm going to do. You know, we talk about reproducible research. Well, we also want to have a reproducible workshop. So in the files that Johnny sent out is the exact same Excel file I'm going to read into Python to run analyses. And it's an HIV data set. There's no PHI in it. So we shared it through email. And I also have code in two formats. One is an HTML file, so you don't need anything special to open it. The other is a Jupyter Notebook file, which I'm going to talk a little bit more about as we get into this. And so I don't want this just to be a coding workshop. I'm really going to talk about general issues. And I also invite it to be interactive. So I know there's a lot of people on Zoom, so as best as possible, Johnny's going to kind of tag team with me to help me if there are questions throughout. I am going to leave time for questions at the end, but I don't expect you to wait till the very end to ask questions. So either raise your hand, put in the chat, or those in the room, please give a shout out, raise your hand. I'll just say one last thing before I go on. The focus today is going to be using AI machine learning tools for secondary analysis. We are going to have later seminars and workshops where we talk more about how to use these tools to develop interventions, be it chatbots or other digital tools. So today, just focusing on analyses. So before I get into the coding and the specifics, I think it's good just to talk about an overall, what do we mean by AI? Let's make sure we're all on the same page. So this is actually a term that goes back to the 1950s. And even though today we equate AI to large language models, the truth is it goes back much farther than those even came into the picture. So just for a broad definition, we can think of AI as simulating human intelligence in machines that are programmed to think and act like humans. And so there's even examples from the 1950s about one is a robotic mouse, which had a light sensor on it and just went through a maze. It would bump into walls or kind of find its way through. So clearly that was long before large language models or any sophisticated computer capabilities like we have now. But even that robotic mouse, you could consider AI because it was doing human-like tasks or mammal-like tasks using a computer program. You know, there's other good examples from the 1950s, checkers and chess playing programs. Some would even consider, even before the term, someone came up with the term, you could go back to machines like the Mechanical Turk, as it was called. It was a chess playing machine, even though there was a human hidden inside that moved the chess pieces, it was fraudulent. It still kind of set the tone for people thinking about creating machines that performed human-like tasks. So when we say AI, it's a very big umbrella. And you could debate with me on terms and usages, but this is as it's generally understood. AI is this umbrella term for computer algorithms carrying out machine-like tasks. And what we're really going to focus on today is a branch called machine learning, where these are tasks that maybe a human could look through patient records, for example, and try to classify patients into subgroups, but instead we use computer algorithms to do this. So today, focus on machine learning, but this big umbrella of AI covers computer vision, certainly large language models. There's a newer term I'm starting to see in the literature more, and that is large multimodal models, meaning we're pulling in vision models, say diagnostic imaging, along with just patient records. That is not visual data, auditory data. So pulling everything. But today, focusing on machine learning. Can't cover everything in one workshop. Let's talk a little bit about terminology, because a lot of times that's half the battle, right? And just understanding the terms. So probably most of you have some sort of statistical background, and that's a good starting point to venture into this space. So if we think about with traditional statistics versus machine learning, and I'm going to use AI and machine learning together because ML is a type of AI, but just know we're going to focus on ML today. If we think about the purpose of traditional statistics, we want to make, to use technical language, a statistical inference, or we wanted to describe a relationship between a set of variables and an outcome. We want to understand what's going on in that relationship. So understanding is really the key. When we get into more machine learning, we also want to understand, but the focus now is more on prediction. Can we predict an outcome? Now, that's an oversimplification because you could say, but what about causal inferential machine learning techniques that also want to untangle relationships? Fair enough. But I think in broad strokes, we can say traditional stats is often focused on description, whereas AI ML is more focused on predicting. With traditional stats, the models are very much theoretically driven. A starting point when we're going to formulate a study or write a paper is we go to the literature, and we usually pick out variables based on what we find in the literature and plug those into a model. With machine learning, we should still do that. That's a good starting point, but it's much more data-driven. It's more exploratory because we want to predict. We want to really drill down and find the set of predictors that best accomplish that task. So more data-driven. With traditional stats, of course, statistical inference, description, we like to attach p-values, confidence intervals to our results, effect sizes. With AI ML, because we're focused on prediction, we're more focused on accuracy. How good is our prediction? Because you can have something that's got a very small p-value and we jump for joy, but it might not do a good job actually predicting that outcome. So understanding the purpose of the analysis and what you need it for, that's really important. So now some terms, with traditional stats, we talk about covariates predictors. With machine learning, we're going to talk about features. A feature is another name for a covariate. Traditional stats, we talk about response variables. With machine learning, we're going to talk about target variables, labels. With traditional stats, we're going to talk about confounding variable. I love this one. With machine learning, we're going to talk about feature leakage. So, each camp has their own terms, and there's whole tables of terminology. I just picked out what I felt were maybe the top three, if I had to make a list of top three. But the key for today is understanding a feature is your covariate, your X, your target response variable. We're referring to the same thing. So here's my promise for you today. I'm only going to show one small formula. I don't want this is not going to be a formula heavy talk. So don't tune me out just because you see a formula on the slide. But hey, I'm a statistician. I can't do a talk and not have some kind of formula on. But I think this will help us to understand what is the difference between a machine learning analysis and a traditional statistical analysis. And the key is in that term learning. What does it mean when something learns? And as a starting point, I'm going to use probably something we're all familiar with, just linear regression. Think about an ordinary least squares regression analysis you might do in Stata or SAS starting point. And so if we think about that, if we think about a traditional statistical model, we plug in covariates. Now, I'm just showing one covariate. Obviously, we would have many, but just for simplicity, I'm showing one in this formula. And what is the goal of an ordinary least squares regression? We want to minimize our squared error, right? So we can write it out in a formula if we've got some outcome y. We've got an intercept term, we've got a beta, and we've got some covariate that we've also going to attach a beta to. So in this model, we've got two betas. We've got an intercept and a slope. And we want to minimize the error. That's the goal of an ordinary least squares regression. Well, how do we make this machine learning? Well, one of the algorithms, which we're going to cover today, is called lasso. We like our acronyms in science, right? And stats is no difference. And so a lasso just refers to least absolute shrinkage and selection operator. So what does that actually mean? Well, one of the key defining things with machine learning is we're going to break up the data into different subsets. We're going to use one to build our model. We're going to use another to iteratively evaluate that model fit as we're building, and then we're going to break out another one into a test data set. And I'm going to show a visualization that this should be a little bit more clear with that. So one of the things that machine learning does is we're going to add hyperparameters or what we call tuning parameters. So for lasso, it has one tuning parameter. And we're just going to call that lambda here in the formula. And so that formula at the bottom of the screen, we still want to minimize the error. But now if you look at the right-hand side of that equation, there is a lambda that's multiplied by the absolute value of that beta coefficient. Now, why would we want to do something like that? What is that extra term in that loss function do for us? Well, here's what that extra term does for us. And I have the formula at the top. If we set that lambda term that we're going to call it a penalty parameter, if we set that to 0, then we have an ordinary least squares regression model. So we can tune and say we don't want any penalty. As we crank up that lambda term, that's going to drive, in this case, our one slope, our coefficient for our one slope variable. It's going to drive it towards 0. So what that means is it's going to have a really strong effect in minimizing the error in order for that to be included in the model. If it doesn't have a very strong effect, it's going to get wiped out And what lasso actually does is it drives the coefficients that for variables that don't make a big impact, it drives them to zero. It zeroes them out. Now, why would you want to do that? Well, think about variable selection. This serves as a variable selection technique and gives you better prediction with fewer variables. So if we think about, there's a lot of words on this slide, but to think about it in simple terms, in statistics, machine learning, there is always a variance bias trade-off. We're always trying to strike that balance. And so what machine learning helps us do, arguably better than traditional approaches, is it helps us strike that balance between bias and variance. If a model is too complex, it might fit that data set really well, but it's not going to perform well in other data sets. And so by having this penalty parameter, what it does, if we have too many parameters in the model, it helps us to trim them, to drive them towards zero. So hopefully that kind of makes sense. I'll pause for a moment. Are there any questions in that regard? We're all good so far. I think Johnny's monitoring. Yes, Johnny. No question. Okay, so we'll go on from there. Let's give a visual. When I said that in machine learning, you break up the data set, what do I actually mean by that? Because for lasso, we have one penalty parameter we want to fit. For other techniques we're going to talk about, there are multiple penalty, hyper, tuning. We're all referring to the same thing, these additional parameters that we attach. Well, if you think about a traditional analysis, what do? You plug in a single data set and you analyze the whole data set and you look at the fit of the model to the same data set you used to run the analysis. So that's, in a way, it's cheating, sort of, because you're using the same data set to both fit the model and evaluate its fit. So we can really think about machine learning where we break up the data into three pieces. We're going to have our training data, and that's the blue box on the left-hand side. And then on the right-hand side, we're going to have our what we call holdout or test data. You're going to see different terms in the literature. So it's often called holdout or test data. And what that holdout data on the far right side means is that once we have finalized our model, we're now going to use a different portion of our data to actually see how well the model fits. So again, this is different from traditional stats where we're using the whole data set to both fit and evaluate the model. Now, a natural question you could ask me, well, how much of the data should I withhold to try this out? There's no wrong or right answer. Common percentages, it's often in the range of 25, 30% of the data you withhold to then evaluate the model and report your performance metrics. So how does the training piece, how does that happen? Well, cross-validation, as we call it, is a common method to train these models. And what do we mean by training? Well, we're going to break the data up into 5 chunks within the training data. And you'll hear in the literature, we talk about training and validation data. So in this visualization, I'm lumping the two together. But what that means by is, if we break it up, this is referred to in this setup as 5-fold cross-validation. And what that means is we break the data up into 5 chunks for our training. And we're going to take that first chunk and we're going to pull it out. And we're going to only train the data on the other 4/5 of the training data. And we're going to come up with an initial model. It's going to have a tuning parameter. It's going to have, in this case, regression coefficients if it's lasso. We're going to fit the model, and then we're going to go to the next iteration, and we're going to hold out now the second piece of the data, and we're going to train using the first chunk in the last 3 chunks. And we're going to repeat this process. And what's going to happen is each time our parameters are going to give us a little bit better prediction. You know, we need a metric to see, is the model improving? Are we reducing the error? in our loss function. So that's the basic idea. There's obviously a lot of details under the hood, but this is just a visualization of this is a classic machine learning approach that takes place. And this is really the distinguishing mark for machine learning. Any questions there? No? Okay. So I've talked about lasso. That's a really great starting point, and I use it a lot. So that's why I put in the slides today. Another one, which is going to be pretty common in your toolbox, or should be, and that's random forest. And what do we mean by random forest? So if we start with the concept of a decision tree, and let's say like today we're going to have a binary dichotomous outcome. We're going to look at depressed or not, depression. And you want to predict the probability of an event or being depressed. If we're talking about a continuous outcome, then we refer to regression trees. So just note that in the literature, you'll see decision trees versus regression trees, but the concept is the same. And what the idea is that you start with all of the data at the top. In this visualization, we refer to this as a root node or an initial internal node. Again, different terms in the literature. And we're going to pick the feature or variable that is going to best differentiate the data based on that outcome. So in other words, if we have, say, depressed, that's the outcome we're going to look at today, or depression. We're going to look through the data, or the algorithm is, and it's going to find the feature that best differentiates the participants based on being depressed or not. And once we find that feature, that's going to be our first decision point. That's going to be the first split in the tree. And that's the child node I'm showing there. And then we're going to go down the line and we're going to find the next best feature that makes the best split. And we're going to keep going. So a term you're going to hear with decision trees and random forest is node purity. And purity simply means that how good is this feature at splitting the data so the outcome is differentiated? In this case, depressed. How good is it differentiating cases who show up as depressed or not? So that's the node purity. And that's one of the metrics that we look at. Now, with decision trees and also random forest and similar methods, we don't get regression coefficients. So how do we figure out which features contributed best to the fit of the model? Well, we're going to look at a classic metric is the Gini impurity. And it's simply how much does this feature contribute to what we refer to as node purity in coming up with decision trees. So even though we don't get regression coefficients, we can still map out and see which predictors or features actually did the best job of differentiating observation or cases. Something I see I forgot to mention from the lasso slide and carrying forward, and we're going to get into this when I give the demo, is do we need to scale our features? And what do we mean by scale? If you think about when we talk about in traditional statistics, standardized coefficients versus not, it's this concept, do we, subtract off the mean? Do we standardize so that the standard deviation is 1, mean 0 for the variable? So that's what we talk about when we say scaling. So for the lasso I was talking about, scaling is very important because if you think about it, it penalizes large regression coefficients. So if your variables are on all different scales, just by way of the range of values that variable can take on, some variables are going to have bigger coefficients. So that wouldn't work very well. So for lasso, we need to scale the variables. And I'm going to show that when we do the Python demo. For random forest, you don't, because you're looking at, again, node impurity. You're looking at how well the features divide the observation. So whether the variables are scaled or not, that's not going to matter. Well, actually, if you scale them, it might make it harder. So it's actually often preferred to scale. So just something to keep in mind. This is a general principle. You should ask yourself, do I need to scale or not? Generally, it doesn't hurt to scale if you're unsure, but on algorithms like random forest, if you don't need to scale, generally you don't want to because it might perform a little bit better if you don't. So this is decision tree. What does a random forest mean then? So the random forest means that we're going to bootstrap our data and we're going to create all these bootstrap samples and we're going to fit separate trees. Now the default in Python is 100 trees. You can tweak that. That's one of the parameters you can shift and see if you get better model performance. And you're going to fit a bunch of trees, and then you're going to aggregate those results. And I should mention that besides bootstrapping the observations, random forest also takes a sample of the features. And there's all intricacies around that, why it does that, because you end up with actually a better model in the end. So just think random forest, we are fitting these trees together and we're aggregating the results together. There's another algorithm we're going to talk about called gradient boosting, or this one specifically extreme gradient boosting. And this one, instead of looking at the trees together in parallel, we're actually going to fit the model sequentially. We're going to come up with an initial tree, then we're going to fit one on top of it to minimize error, impurity, and improve it. So these are two common algorithms, random forest and gradient boosting. You'll see a lot in the literature. And so as with lasso, we had one parameter. With these tree, random forest, gradient boosting, there's going to be multiple parameters we can tweak to grow the trees in different ways. Beyond the scope of today, but it is worth an honorable mention. I actually almost debated trying to squeeze this in, but I looked at the number of slides and I said, yeah, no way, it's too much. But the principles will still apply. Maybe we'll do another workshop on it. I don't know. Is you get into what we call as deep learning. And we can start again with the concept of a linear regression. And again, we want to equate our outcome to X through some parameters. Now, if you fit just a regular regression, the number of parameters closely match the number of features or predictors. What deep learning does is that, let's say that we want to model complex relationships between our features. You know, with traditional statistics, we usually just throw in an interaction. But if we want to take a more data-driven approach, we might let the data tell us what interactions are present in the data. And in order for it to do that, we actually introduce what are called hidden layers. Now, I'm giving this in very high terms, so I don't expect you to think about the mathematics of this and drill down, but just to show you a visualization, what do I mean by a hidden layer? Well, what that means is we still have our observed features, but now we're going to put in some interactions, as you can think about them, or some additional parameters to model complex nonlinear relationships between the features and what we call the output layer or our outcome. And so that's when we get into deep learning. That's what that means. And so that's why, you know, if you read in the literature about, say, large language models, which are based on these neural networks, they'll have in the millions, maybe billions of parameters. Well, that doesn't mean those all represent observed data points. It means here are all these layers, these hidden layers of complex nonlinear interactions that are taking place. And so, of course, you need data sets in the millions. Another reason I didn't do that today, because I'm using a data set of about 1,000 participants, so too small to fit a model like this. It wouldn't make sense. But I want you to know about this if you want to look into this. It still fits in that machine learning framework. You still have tuning parameters. All the principles I'm going to talk about today, they still apply to deep learning algorithms. So everything builds. And this is probably a good point in the workshop to just say, no matter what methods you end up using, the study design principles remain the same. Always use good design principles. That doesn't change. And I really love this paper I came across in JMIR. It just lays out a nice visualization to kind of show what's different about machine learning. How does this change up the basic study design? And it really comes down to, in the middle there, you've got this hyperparameter tuning piece of the analysis that you don't have with traditional statistical methods. But please always follow good practices. You know, I hear sometimes students will come to me and they'll say, I know NIH likes AI. I want to work that into my proposal, right? We're all guilty of that, not just students. I do this myself. We want to work that into the proposal. And in the first thing I ask, well, what is your research question? You know, is AI even called for? So as much as I love AI and machine learning, I don't always use it because please always let the research question drive the analysis, not the other way around. So that's my caveat to that. I wanted to at least say that. So before we get into the actual coding, I do want to give another overview. I'm kind of peeling back the onion today. I started talking about there's this AI umbrella, and then we've got machine learning as part of that umbrella that this fits into. And then even with machine learning, that whole concept of learning, you can ask, well, how does it learn? What are some of the methods of learning? So today we're going to talk about a very specific type of learning we refer to as supervised learning. And this simply means that we have labeled target data. Like today, we have participants where they received a depressed or not depressed screening from the assessment, and we want to develop an algorithm to predict future events of depression. So we have labeled data to start, so we refer to this as supervised. And all the methods I'm going to talk about today for the workshop that I'm going to show you coding for, these all fall into that supervised learning class. And why am I doing that? Because arguably in medicine, HIV research, supervised learning is by far the most common. So that's why it's a really good starting point. But having said that, it's worth it for you to just have an understanding as where does supervised learning fit in to this environment, because you're going to see these terms in the literature. So I at least want you to be familiar with them. If we have supervised learning, it's natural to have unsupervised learning, right? So I like dogs and cats, so I figured, you know, I picked this picture. I got this from this website. And, you know, for an unsupervised learning algorithm, we can think about, let's say we have images of dogs and cats, and we don't know they're dogs and cats. And we say, I want to classify these animals somehow. Can you help me classify them? So we can run this through a clustering type algorithm. And the algorithm can actually help us classify cats as cats and dogs as dogs without having labeled data to begin with. So that's the idea of an unsupervised algorithm. Obviously, not applicable for HIV research. You could think about cases if you have medical images in the field of virology, where maybe you don't know how to classify them. So you throw the images in and you start with a classifier. So that's more of an HIV-focused application. There's another type which it's kind of a gray area. You could kind of call it unsupervised. I think it's really cool. So I wanted to put a slide in on it at least. And that's this idea of generative adversarial networks or adversarial learning. And this is example I'm showing here. Let's say we do have training data now, and it could be, again, it could be medical images in thinking about HIV in a clinical setting. It could be you start with medical images, that's our training data, but then we also, on the other side, we just have noise, and that's what we start with as our generator. That's what's going to generate some synthetic data for us. And what happens is the algorithm now, it looks at the images and tries to replicate those images in this noisy data that's just points, nothing there. Those initial images it's going to generate are going to be really bad. It's going to do a horrible job. They're going to be very grainy. So what we're going to have besides the generator, we're going to have what we call a discriminator, and it's going to look at the real images, it's going to look at the generated images, and it's going to try to distinguish them. Now, initially, it's going to easily distinguish them because the generated images are going to be horrible. But this algorithm iterates, as it iterates between the generator and the discriminator, and they play off each other, you're going to get to a point where the discriminator can't tell the difference between the generated images and the real ones. So why do we want to use this technology? Well, where could this come into play in HIV research? One area you could think about health equity. Let's say that we have underrepresented populations and we need to generate more cases so that when we run these training algorithms, we actually have more representation. That's one example. Another one is, let's say that we want to train clinicians and we want to show them medical images, let's say maybe radiologists, but we don't necessarily want to show them images from actual patients. We don't want to worry about PHI. Well, if you generate medical images through a GAN, you can actually get really good lifelike images. And so those are some examples around health equity, data privacy, where GANs can do a really nice job in helping you out. The last one I'll talk about before I move on, and this is another cool one, it's called reinforcement learning. And the classic example is with physical AI or robotics. And that's if you think about how does a child learn to walk? Well, they make a lot of mistakes. They're awkward in the beginning and they fall. They try to get up and put their hands out and they try different things. You can find tons of YouTube videos of robots trying to learn how to walk. Well, that's reinforcement learning. The algorithm tries different things. The reason why it differentiates from the other algorithms, unlike the least squares regression or lasso I showed you, you don't have a clear loss function where you can just plug in features and say, I want to minimize the loss function, help me do that. You have a complex task, learning to walk. So the best way to do that is to let this physical AI fail a lot and try different things out. You do have a reward, the reward or goal, you tell it, I want you to learn how to walk. That's your objective. But it's hard to know how to get there. And so that's reinforcement learning. Now, that's physical AI. You might say that's not very useful for me in HIV research, but there are some cool applications I'm starting to see emerge in the literature. Let's say that predicting disease onset when we don't have clear-cut features. We need to figure out how does this actually happen. And by the way, reinforcement learning is part of what's used to train large language models too. So if you end up developing your own, that's a part of that. So now I've covered, these are the basic types of learning. Now I'm going to get into modeling issues before we get into the coding piece. But let me stop for just a moment. Any questions? Anybody? No questions? We're good? Okay, we'll keep going there. I want to talk about now, before we get into coding, just general modeling issues that regardless of the type of learning that you do or use, regardless of the algorithms, these are modeling issues that are going to pop up. And they're certainly there with traditional statistical analyses, but you could argue maybe they're even more relevant or problematic when you get into machine learning at times. And the first one is with missing data. Now, why is that more problematic for machine learning? Well, let's think about what we do in a traditional statistical analysis. We typically use multiple imputation, right? You impute numerous data sets, you impute values in those numerous data sets, and then you aggregate the results. And because you're estimating the same regression coefficients across data sets, it's fairly straightforward to aggregate those results. Well, let's think about now what we just talked about for machine learning, how that takes place. If you think several slides back, we use cross-validation. And so then we had multiple cross-validated data sets. Think about if you had to use multiple imputation on top of it. Now you're going to what? For each cross-valid data set, you're going to impute. And to add to the complexity, if you use something like lasso and you multiply impute, what happens if each data set picks different sets of predictors or features? How do you aggregate that? Because remember, lasso is a variable selection methods. It's going to drive some coefficients to zero. So how do you aggregate results? It's more difficult. So what do we do in machine learning context? Well, I can tell you by far the most common method is to use single imputation techniques. Now, you might step back in horror and say, I thought in our stat classes we learned that's a no-no. You don't do single imputation. So a couple of comments on that. One is we are working with very large data sets. So we are going to underestimate the variability a bit, but the notion is using large data sets. And so even if you run traditional analyses, if you think about in health policy management, we often work with large administrative data sets like MEPS, California Health Interview Survey. They often use single multiple imputation for those, and they do something called hot decking, where you try to find a case that somewhat matches the case with missing data to replace the missing value. So it is done, even in traditional statistics. It's just we tend to do it with very large data sets, and so it makes more sense. Another reason is that if you are focused on prediction versus obtaining p-values where the standard error is very important, we're a little bit less worried if we underestimate the variability. Not to say it doesn't matter. It's just, it's not the priority all the time. Now, having said all that, and I'm going to demonstrate a single imputation technique in the coding part of the workshop. Having said all that, it's not to say you can never multiply impute. Certainly, I attended a few weeks back with CHIPS. We had maybe not a few weeks now, a little bit farther back, with Dr. Christina Kitchen, professor in biostatistics. She gave a wonderful presentation on epigenetics and talking about random forest type algorithms, and they certainly use multiple imputation. So that was a beautiful example where it worked well in that case. So not to say you can't do it, it just adds complexity to the algorithm. And if you look in the literature, I think it's fair to say single imputation methods are very common. Another issue, we're not looking at p-values, or not most of the time. You can get p-values out of some ML algorithms, but most of the time we're not looking at that. We're concerned with model performance. We'd say prediction accuracy. So there is an issue with that, though, if we're looking at prediction accuracy. And let's just look at this table here. Like I told you, we're going to look for outcome at being depressed or not. And let's say if most of the participants don't screen positive for depression. Now, this is a data set here with 1,030 participants. And, thinking about good epidemiology, we put people into in this contingency table. We think about our true positives, true negatives, and, we put them into one of the boxes. Well, if we think about accuracy, what does that mean? Well, we could use just our common metric for accuracy, which means how well does the model classify people correctly? We could look at the number of true negatives and the number of true positives, which are the values in the diagonal. Well, if most of the cases are negative to begin with, what is going to be the best model? Well, the best model is possibly one that always predicts people to be negative, right? If most of the cases are. So if we just calculate accuracy here, we say, wow, we got 98% accuracy. What a good model. Well, no, obviously it's not, right? So we need to penalize ourselves with performance metrics and actually not just look at one box in this contingency table or cell. And so there are other metrics that account for imbalances in the data a bit better. One of them is called balanced accuracy. That's simply the average of sensitivity and specificity. And so if we look at this table now and we look at balanced accuracy, it penalizes us a bit and it brings down that accuracy to 0.75. There's also others. There's Matthew's correlation coefficient, which that's a favorite of mine. You can think about it like correlation. It ranges from -1 to 1. A 0 meaning it's like a coin toss. The model's just guessing. And you really want to get close to 1, meaning your predictions and your actual observed values are very well aligned. We can also look at area under the curve because that gives us over a range of values to really give us a better idea of what's going on. Now, we are focusing today on binary outcomes, being depressed or not, but that's not to say that everything I'm talking about today doesn't apply to the continuous world. So it applies there as well. So if we have a continuous outcome, we focus more on reducing the root mean squared error or mean absolute error. And in fact, in the data set I'm providing, I think I even have a variable, a continuous outcome variable, if you want to tinker around with that, even though I don't have time to cover that in the workshop. The last thing I'm going to talk about as far as modeling issues, not the last, second to the last, which is really important if we think about health equity. And that is imbalanced data. And what do I mean by imbalanced? Well, let's say that our depression rates, as I just showed you, are really low. So again, the best fitting model on the surface can be one that just predicts nobody's depressed. Obviously, that's not going to do a good job. So sometimes we don't want to just look at performance metrics that try to make adjustments. We actually need to adjust our data so there's better representation from what we refer to as minority classes. And there's different algorithms. One of them I'm going to show today in the workshop is just called SMOTE. It's kind of a cute name that just stands for synthetic minority oversampling. And as the name implies, it means we look at the minority class in our outcome, this case being people who report depression, and we're going to resample and add new cases to our data. So what that does is it gives the training data a better chance to look at these minority samples to come up with a better model that can fit people across the board, whether they're depressed or not. Now, we don't want to balance the test data. That's an important point because we still want to know how well our model performs in raw test data. If we just balance the test data as well, that's giving ourselves or our model an unfair advantage. So we do want to balance the training data, not the test data. One last issue I'll talk about, we're getting to a good stopping point. We're hitting the hour, so I'm going to talk about one last modeling issue, and then we're going to get more into the nitty-gritty with Python and in the software. But this is also a huge issue. It's model explainability and balancing complexity with explainability. And explainable AI is just a growing field, which as it should be. And just to give you some general principles, use simpler models when you can. Like in the example I showed you with neural networks, do you need to use a neural network? If you do, and you have millions of observations and you find it does a much better job at predicting, then use it. But if you can get by with simpler models, do so, right? What is that George Bach saying? All models are wrong, some are just more useful. So think about how useful is the model going to be. Even if you use more complex models, try to find metrics to understand the model. So as we venture into the random forest space, we venture into the neural network space, we no longer get regression coefficients we can interpret, but we can look at things like feature importance. In the decision tree, we talked about node purity. We can see how much does this variable contribute to differentiating cases, even if we don't get a regression coefficient for it. So those are really important things. So I'm going to give us all roughly a 5-minute break, where this is actually kind of where I hope we'd be. That rarely works out, so I'm glad that did. So the next hour now, we're going to get more into the specifics about what are software considerations and what is the code and how you use it to do these things in Python. So I'll be on standby. I'll give everybody in the room a break, and if you need to take a bio break, please feel free to do so. All right, we'll go ahead and jump back in. It's been about 5 minutes, so I want to make sure that everybody has a chance. So for the second part of the workshop, I'm going to get more into the specifics with how do you actually run one of these machine learning analyses. And again, just to mention, this morning, Johnny sent out some files. One contains the CSV, or tab delimited text file, that contains the data I'm going to use for the workshop. And the other two files contain the code. One is HTML, which you can open without any special software. And the other one is an actual Jupyter Notebook file, which was generated by Jupyter Notebook. So first, software. Why am I using Python today? And I first want to say I don't always use Python. Use the tool that's the most appropriate. Python is a sledgehammer. It's really powerful. It can do things that no other software can, and especially if you want to integrate your algorithms, say, into website interfaces so other people can use them, you want to use Python, hands down. I like R a lot. I use R, and everything we're doing today can be done in R. And the cool thing with Python and R is, in many ways, being object-oriented, they operate very similarly. So if you understand one, you can pick up the other. I still like Stata and SAS, use that for some things, nothing wrong with it. So just use the most appropriate tool. I'll just say, as far as idiosyncrasies with R and Python, with SAS and Stata, everything comes prepackaged. The idea with R and Python is you install the libraries you need. So it can be very scaled down if you don't have a lot of memory on your laptop or other computer. And so you install what you need. So that comes with some difficulties, but the general idea on Python is you go to your command prompt, and there's commands called pip install, and then you put the name of the library. So I'm showing an example here with XGBoost, or extreme gradient boosting. It's the one we're going to use today. So you first have to install it from the command prompt, and then when you open up your session, you always have to instruct Python, I want to use this library. So you then type import, and there's some common representations, like we say import XGBoost as XGB. You don't have to use XGB, but these are just some common ways people do it, so it's easier to share code. And you always know when you see XGB, oh, this is what it's referring to. If you forget to install, I do that all the time, you'll get a friendly reminder that'll say this module is not found. So then you just go back, you go outside the session, and then you install. So it's worth noting, too, that all the libraries we're using today are very straightforward. When you get more into the deep learning tools, you're probably going to want to use things like PyTorch. Some of these libraries require you to configure the installation for your particular system. And so I just have a screenshot showing that here. Another thing to note, if you're in the School of Medicine, you need administrator level permission to install things on your laptop, because they don't want you just installing anything. So you can't just go to the command prompt and install. You have to be in administrator mode. So as a word of advice, kind of get all your libraries lined up you need to install at once, then reach out to Digit. You don't want to have to go back and forth and say, oh, wait, there's one more library. So just make sure you've got everything lined up. Another a decision point when you're going to run Python. Do you want to run it locally on your machine, or do you want to run it in the cloud? And I know GitHub is a common cloud-based environment a lot of people use for Python coding. Like anything, there's pros and cons. The nice thing about running it locally is there are fewer security issues. And so Digit School of Medicine is going to be happier with you if you run it locally. In fact, they will block you if you try to run through GitHub. At least that's been my experience. You can't. So that's just something to keep in mind. So why would you want to mess with GitHub? Well, outside of our secure system here, you can run Python from different computers and you don't have to reinstall the libraries each time. You can have different computers because it's in the cloud. Another benefit is GitHub has Copilot, and so it will help troubleshoot your code as you type. There's other distributions that do that as well, so I wouldn't let that be your decision point, but it's a nice feature to have Copilot. I just have one screenshot showing I make mistakes all the time coding, so it's nice to have a chatbot to correct me, as GitHub kindly did here when I left out. I forgot what I did on this one. I think I put quotes in when I shouldn't have. Instead of typing none, I put quote none, and so it corrected me. It did a good job. Just one note on coding though. Some people like to use it to code from scratch. I'm still wary about that for statistical analyses. I know people have differing opinions. I'll just say in reference to coding from scratch, I really like this from Seth Berry. Never trade cognition for convenience. So even if you code from scratch, you really have to understand what is it coding? Is it properly coding missing values? Because it doesn't know. So that's my 2 cents on coding from scratch. So today, for this workshop, I'm going to go with local distribution. I installed Python on my computer because I would have been blocked otherwise, wouldn't have been able to present for you. So that's why I went that route. There's different distributions. I like Anaconda. You can just Google Anaconda Python. There's the link. You don't have to use that one. There's many different. I just like Anaconda because I feel like it's user-friendly. It's got a nice web interface, and it also comes with Jupyter Notebook, which a lot of classrooms use Jupyter Notebook. And here's the Anaconda interface. You just click on Jupyter Notebook, and it's there. I just find it's very user-friendly, so that's why I like it. Okay. So here's why you came today, the actual analysis demo. So let's get into it. So we're going to use an HIV data set. This is from a study called ATN CARES. And I see one of the PIs, Dr. Swendeman, is on the call. And this was a study, and Dr. Lee was also part of this. He actually led the recruitment efforts, so we wouldn't have this data set otherwise. And so this was an NICHD-funded study. It was multi-site. It took place in Los Angeles and New Orleans. There was 3 suites of interventions, and one was for acutely infected or treatment-naive people living with HIV. A second one was for people with more established infection. A third one was for people not living with HIV, but considered to be at high risk. And for this workshop, we're going to use the baseline data, which is comprised of 1,722 study participants. There's some citations. The outcome we're going to focus on for this workshop is PHQ-9, which is a 9-item depression screening tool. I dichotomized it using a very common split, where 1 represents moderate to severe depression, 0 equals none. I left the original continuous variable in the Excel workbook, so if you want to try these models with continuous outcomes, you can do so as well. And then I picked out some features or predictor variables we're going to throw into the model. This is certainly not an exhaustive list. I purposely kept the number of variables small just so it's easy to see on the screen in the code. But you could certainly, normally you'd probably use many more variables. And I also picked this list of variables to show you kind of data wrangling with different types of variables. You know, some have multiple categories, a few continuous, just to show you the messiness of what you deal with. I didn't want to just give you a clean data set. I wanted to see you kind of, you know, how do you deal with messy data in Python? And so, you know, if you think, again, going back to research questions, if we think about, if we just wanted to know which variables were associated with depression, possibly to develop intervention targets, you know, which variables do we need to target in an intervention, maybe a traditional statistical analysis would suffice. You know, we wouldn't need to do a machine learning. But let's say now we want to predict depression from the variables we collected. We want to know, did they predict it? And if so, which variables best predict? And now the motivation could be, maybe we want to come up with an automatic detection tool. I know like Hal wants to develop AI-driven chatbots, right? So if we have an automatic detection tool, we could ask a participant to enter info in for a few variables into the chatbot. That could feed that into the algorithm, and then that could predict this person has high acuity. We need to refer them for services. So that's just one example. So for that case, probably I'd lean more towards machine learning, which is what we're going to do today. Jump right into it with code. So what are we looking at here? So as I mentioned before, the first step is every time you start a session, you have to import each library you're going to reference during that session. And so every time you open the session, you have to rerun this code. So this is assuming you've installed the libraries. That can be a little tricky, again, if you're working with a UCLA laptop and it's locked, you need to get Digit involved. But this is assuming you've installed the libraries. At the very top, commented out, I have a list of all the libraries I used today. So that should help you. There's NumPy, Pandas, Seaborn, Scikit-learn, imbalanced learn, stats model, and XGBoost. I'm pretty sure that covers all of the libraries. Sometimes I forget what I've installed, but I tried to do an exhaustive evaluation of what's needed to run this. And I'm not going to go through this line by line, but I tried to comment too on what each library is used for today. So that's really our first step. You import these. And then the next step is we read in our tab delimited file. Now, little idiosyncrasy with this is the same for R is, you know, traditionally in folder structures on your computer, you work with backslashes when you refer to files. With Python and R, it's forward slashes. So that's the first thing you'll get an error message if you don't do. And then we simply read it in. Now, this code I'm sharing with you, this is where I read the data in from. Obviously, you'll need to change the location to wherever you're reading the data into Python from. But the PD dot is referring to the pandas library. So whatever you said import as, and you specified pandas, I specified as PD. And again, I'd highly recommend use common conventions because it makes it easy to share code with others. PD is a common convention in referring to pandas. And pandas is just a very nice data manipulation library that you can do a lot of stuff with, including reading in tab delimited files. Just like I would do with any analysis, even traditional, I always like to familiarize myself with the data. You know, what does it look like? So there's three sets of commands to print. The first one is to just print the length or look at the dimension, how many observations are in the data. So you see there 1,722, which is expected. You can also look at the columns and print the column name. So that's the next command I did. So if you look at it, it says index, it's got study, age, race cat, gender cat. So those are all the variable names. And then a nifty command I like in Python, you can tell it to print the first 5 rows in your data set. And I've also done that because I just like to look at the raw data. I don't want to just look at summary stats. And so this kind of gives me an idea of what's actually in this data set. What do the observations look like? Now, of course, we also want to look at summary stats. You just want to get an idea of what's going on here. So this is simply more code to just look at summary stats. And we're going to start with frequency tables for our categorical variables. A couple things to note with our categorical variables. One is that if you look at the middle column and last columns, you'll see an NaN. That's missing values. So that means, you know, for example, for that hospitalized for mental health or hosp MNT variable in the middle, it has one missing value. So that's something we're going to have to deal with when we wrangle the data. That's just to let us know. Another thing we're going to have to deal with is that, and I purposely did this, I could have dummy coded ahead of time, but why would I spoil the fun there going through that process? We have some categorical variables with more than one category, so we're going to need to dummy code those in order to enter them into the analysis. And not just dummy code them, we're going to have to put them as 0, 1 numerical values. We can't analyze categorical or text data. So just a couple things to keep in mind as we're looking at this. And then I also want to print out my continuous variables using our typical number summaries, mean, standard deviation. And so in this data, we've got two continuous variables. We've got age, and we've got a emotional support, just meaning do you have emotional support, with higher values indicating more support. So we've read in the data, we've looked at a summary, and let's get to work now. Let's do some data pre-processing. So the first thing is let's dummy code. So in the interest of time, I'm not going to go line by line through each one. I'm just going to talk about the code generally. But I'll just say some things to note is that one popular command that's part of the libraries that I read in is called one-hot encoder. So if you Google one-hot encoder, there's all kinds of documentation about that. And that's just a fancy way to say it will take a categorical variable with text categories, and it will convert that into multiple 0, 1 dummy-coded variables for you. So that's what one-hot encoder does. For our binary variables that already have two categories, those were text variables. So we just need to convert those to 0, 1. And so I also have that code here. So there's two steps. I'm using one-hot encoder to create dummies. And then I'm also converting the binary text variables into dummies. And then I'm combining them all into one data set, which I'm going to use. And if you notice now, again, I use PD for pandas. So pandas is a very common data wrangling library we're going to reference. And we just need to put PD at front when we use the command like concatenate. Otherwise, Python won't know what concat is. We have to attach it to the library. And again, we're just going to print out the first 5 rows to just check that we concatenated and everything is there for these variables that we wanted. I'll make one important comment here about one-hot encoder and dummy coding in general is that for machine learning, we do not have to create a reference category ahead of time. Now, that might seem perplexing to you because for basic stats, we always create a reference category, right? So if we have, say, our study variable, we have study 1, 2, or 3, we would normally make one of those categories a reference category, and we would only have 2 dummy-coded variables. If you notice, I did not drop any of those 3 dummy-coded variables. There's study 1, 2, and 3, and I did that for the others. Now, you might say, why are you doing that? That doesn't make any sense. Well, what the machine learning algorithm is actually going to do, it's going to pick the reference category for us. It is going to force one of those variables to 0. So you could dummy code yourself a priori so that one of them is set to 0, but I can let the machine learning algorithm do that for me. Why would I do that? Well, one benefit is the algorithm might actually drive more than one of the dummy coded coefficients to 0. It might say, you don't need this variable either. It's really going to let the data tell us what we need. So that's why I put all of them in and really let the model do that. Another step I mentioned earlier, there is some missing data in here. And so we're going to use imputation. We're going to use single imputation. And so a popular library for that, or not library, command that's attached to the libraries, is we're going to use KNN imputer, which that just stands for nearest neighbor. And what it does is to impute, it's similar to hot decking in that it will look for neighbors or other cases where the values are similar enough to the case with the missing data point, and it will grab a value from one of those cases. Now, when I set this to n underscore neighbors equals 5, that's telling the algorithm, I want you to find the 5 nearest neighbors. And it's going to then average over the values it pulls from those 5 nearest neighbors. Now we're going to do one additional step, and that is that, if you have a continuous variable and you just average over those 5 values, it makes sense, right? If you have a binary variable, we don't want to end up with a proportion. We want to actually force it to either go to 1 or 0. So there's an extra step in here where we're going to do that. We're going to round. And that's what you see in the code, why I rounded. That is for that case. And then I'm just going to check to make sure my imputer worked. It's always a good idea. So I just looked at the first 3 variables here for illustration. I put it on the screen, and we can see, lo and behold, the imputed values are now filled in. Also a good idea, we want to check our multicollinearity. We want to do a matrix of correlation coefficients. As we look at this, I know it's kind of small on the screen, but it's just showing that, except for the variables that are dummy coded that we would expect to be correlated with each other, overall, the correlation is not bad. If you get correlations that are, say, in the range of 0.6, 0.7 in magnitude, then we might start to worry that the correlations are a little bit high and we should either drop one of the variables or use one of the machine learning methods that can handle multicollinearity better. So, but always check correlation matrix. And there's one more technique I'm going to cover a few slides down that would be on the pre-processing side, but you'll see why I pushed it down. So I'm going to cover 3 machine learning methods. I was trying to, again, try to strike that balance to not cram in too much, but to whet your appetite with enough methods. So we're going to start with a logistic regression as a starting point with, again, depression as our outcome. And then we're just going to cover 3 machine learning models. We're going to cover lasso, random forest, and extreme gradient boosting. And I picked these models because these are probably where I would start most of the time for binary outcomes. There are some tweaks to lasso. You could say, what about elastic net? What about ridge regression? There's other tweaks to these, but these are really good models to start with and end with as well. Let's just start with the standard regression. I'm not going to dwell on this slide too much other than to say, with Python, you have to specify that you want to add a constant for an intercept. It doesn't do that by default. And then you can run the model. And so we get output like we would in SAS or Stata. And again, I'm not going to dwell on this for too long. This is standard statistical output you would see. Now let's rerun the same regression. And let's just use a machine learning module we're going to use. So it's the exact same regression, no penalty parameters yet. I just want to get us accustomed to, let's use a different module that we're actually going to use to do some of these ML analyses. And so for that first line of code, we're telling it just run a logistic regression for me. We're going to use a Newton-Raphson type algorithm to find the parameters that we would do as a standard regression. Penalty equals none. We don't want to put a penalty parameter in. We're going to use random state because we want to be able to reproduce the results. So we specified the model. In the second line of code, we're going to fit the model, and then we're going to spit out coefficients. And the coefficients are going to be very similar to what we got from the prior analysis doing the other module. So now let's get into the actual fun stuff here. Let's see. Oh, not quite yet. Let's get in. This is fun. Don't want to get ahead of myself. So we've refit this logistic regression model using a machine learning module, but it's the same model. And so now we want to start looking at the performance of the model. We're going to see how did it do. Not just looking at p-values, but looking at more performance-oriented metrics. So up near the top there, where we've got train test split, that is a common module that people use to split up the data into training and test data for machine learning. There's a command there, size equals 0.3. That's simply instructing Python to set aside roughly 30% of the data for testing. And we're also going to stratify, and what that means is it stratifies between the training and test data to ensure that we maintain about 30% of the observations of people, it's saying we maintain the same number of depressed cases, or the same proportion of depressed cases in both the training and test data. So in other words, if we just say randomly pick 30% of the observations, we could randomly pick cases where nobody's depressed in the test data, and then we wouldn't really be able to evaluate the model. So by stratifying on our outcome, it's saying let's make it balance between the training and the test data, and that's just showing you on the right, it actually did that. And so then going down in the code, we're going to specify our predictors or features we're going to plug in. And then at the very bottom, we're going to look at some common metrics. Now, this is not an exhaustive list of metrics. These are some common ones we'd use for binary data. Certainly people look at F1 scores. There's other ones, but these are some common. So if you look at the first row there, accuracy, it's around 72%, the 0.715. If you look at area under the curve, it's 0.73. Now, if you notice the balanced accuracy, it dropped. And that's because the ratio of depressed cases in our data, it's less than 50%. So the balanced accuracy is not going to match the accuracy. It probably gives a fairer picture of what's going on. And then again, Matthew's correlation coefficient ranges between -1 and 1, 0 being a coin flip. So 0.23, we'd like it a little bit higher, but it's, it's not a coin flip. And so these are some metrics we printed out on the bottom. And one other thing I'll mention before moving on to the slide. So you'll notice, whereas we plug in our training data to fit the model, when we get to printing out our metrics, we're actually going to use our test data. So you'll see X_test1. So in that, again, is because we don't want to, we could look at the accuracy in our training data as well, but that would be more like a traditional statistical analysis. We really want to see how are we performing in a piece of the data that we set aside? So we've done this initial logistic regression, and this is going to be a kind of a benchmark. We're going to compare our machine learning analyses against it to say, are we doing better than just fitting a logistic regression? Now, one more pre-processing step, and I purposely put it at this point in the slides, and that's addressing class imbalance. So in this data set, there are fewer than 50% of the cases that are screened as being depressed. And if you look at the top there, there's 359 that's screened as depressed. This is using the SMOTE algorithm to rebalance the data. And so that now if you look after SMOTE, you see what it did was it took that minority class of 359 and it added synthetic cases. So now there is 846 cases in both categories for depressed and not. Obviously, if you are doing a randomized controlled trial and you have to make a consort diagram, this wouldn't fly because people go, what are you doing? You can't increase your sample size artificially, right? So this, again, this is a machine learning technique we use when we want to improve the predictability of the model, especially when we have some classes that are not represented adequately. The reason I didn't move this slide earlier is because I want to show you how to do SMOTE, but because I want to benchmark the machine learning models against our original logistic regression, we're going to actually set this aside. We're just going to run all our analyses on the original data. But if you were going to do a true machine learning approach, you might choose to use this inflated data set that has these synthetic observations in it. Another step, though, that we are going to do throughout the rest of the workshop, and that is scaling features I talked about, or setting the mean to 0, standard deviation to 1. So this is very important for lasso, which is the first method I'm going to demonstrate. We absolutely need to scale to make it a fair comparison when it penalizes. And so again, it's seemingly a lot of code here, but a lot of it is I am specifying the variables that I'm going to include in both the training and test cases. And the actual code to do the scaling, there's a module called scaler. And we're choosing standard scaler. You can use different scalars. I want to set the mean to 0 and standard deviation to 1, but there's different scalars you can use. And so if you look at the arrow pointing to the right, again, always check your data. I just wanted to check myself and see that if I look at age, for example, I look at the age variable and the count in the training data for the age variable, there's 1,205 cases, because again, it's not the whole data set, it's the training. And I look at that and I say, okay, in the original data, participants had a mean age of about 21 or 20.9, standard deviation around 2.1. The minimum was 14 years old, the maximum of 24. And this reflects the eligibility criteria. Look at what happens after scaling. The mean, it's not going to be exactly 0. It's minus 2.21. This is scientific notation out to the minus 17. That's very close to 0. And if you look at the standard deviation, it's very close to 1. So scaling worked. It accomplished the goal. Johnny, any questions I haven't asked for a little while? We're all good? Okay. So now let's actually get into fitting a machine learning model. So we fit logistic regression. We did it in a standard module. Then we shifted over to a machine learning module. Now we're going to use that same machine learning module, logistic regression again, but now we are going to introduce a penalty parameter. And if you remember on earlier slides, this was that lambda where we penalized large coefficients. We penalize model complexity. And we're specifying in the model here, the key term is where we have penalty equals L1. L1 means we want to do a lasso regression. If it's L2, that's ridge regression, or we can specify elastic net. We can do both penalties. An important modeling point for Python, what you are specifying with the penalty parameter, you're actually specifying the inverse of lambda. So you're specifying what they refer to as C, which is 1 over lambda. That's important to note because the penalty parameter, as it increases, the penalty is higher, but with C, it's the inverse. So as the penalty parameter gets closer to 0, that's a bigger penalty. So that's really important to note. Always know when you fit these modules and softwares and algorithms, understand what you're plugging in, because it can just drive you absolutely nuts if you think it's one thing and it turns out to be something else. So we're going to fit the model. Again, we're using our training data, and we're going to tell Python, I want you to spit out the coefficients. And we want to take a look at this. So let's spend a few moments in dwelling on the coefficients here and see what it actually did. So you notice it's got the coefficient values and it's got the intercept on the bottom, which we don't care about that so much. But now we notice a difference from the prior output. Notice that 3 of the coefficient values are set to 0. So which values did it set to 0? Well, if you go back and look at, you can go across the row and see the dummy coded variables I specified. The model actually chose reference categories for us. If you remember in the data, we have 3 categorical variables with more than 2 categories. We have our study variable, we have our race ethnicity variable, we have our sex gender identity variable, which, disclaimer, that's not the best way to do it. Obviously, in a full-fledged analysis, we would probably not. It's better to separate them out, but we are mashing them together and doing one multiple category variable. And so there was 3 of those. So therefore, we're going to have 3 separate reference categories for each of those. So that's what this model is doing. So you might say, well, the model didn't really do much for me. I could have done this myself, right? So why am I illustrating this model? Well, I just want to give you a starting point. Because in truth, that penalty parameter that Python is doing by default, which is it sets C to 1, that's a pretty weak penalty parameter. So the only thing it did was it just drove the reference categories to 0. Now, obviously, if you just did a logistic regression and there was no penalty parameter, the model would crash, right? You'd have multicollinearity. But because we have some penalty, it's actually able to drive the reference categories to 0 at least. And then if, again, we're going to look at the accuracy each time we do a model, we actually don't see any gain in accuracy, which is not a terrible surprise, right? Because we didn't do anything. All we did was let the model choose reference categories. So now let's get into something more fun, and this is what I would actually do. I wouldn't just pick a weak penalty parameter. I wouldn't pick it myself. I would let the model choose. And so we're going to do cross-validation. And, values of 5 and 10 seem to be common. There's no golden rule. The more you cross-validate, probably the better your estimates are going to be, but it's always a trade-off with computational speed and all that. So I just chose 10. So that's what the CV equals 10 means. Again, we're going to specify an L1 penalty, which is lasso, but now I'm going to let the model choose what that value of the penalty parameter should be. And check it out now. This is pretty cool. If you look at, you see a lot of zeros here now. Look at how many parameters it drove to 0. And what's really cool about it, look at our accuracy and other statistics. Now, you might say the accuracy didn't improve, but think about what we're doing. We're reducing the number of features, and we're actually getting comparable accuracy to what we had before with all these variables in the model. So again, think about practical applications. If I am say again, like with a chatbot, and I want to put screening questions in, I want to put in as few questions as needed for people to fill out, right? And so doing some variable selection and trimming down the number of variables I need to get a reasonable level of accuracy is a plus. Now, in this case, an accuracy of 0.73, I'd probably want that higher. I'm just using this for illustration purposes to say we didn't see a drop in accuracy when we reduced the number of variables. Another thing you should always do, just like with traditional stats, we should look at the coefficient values, even though these are scaled variables, and we can at least look at the direction to see, does the direction of association make sense with our outcome? So that's still important. And that's what I put some notes to just explain the direction of association. Why does that make sense? So for example, that very first one, study 2 enrollment, being in study 2 is negatively associated with depression. That's more an artifact. It's not to say having HIV is associated with being less depressed, but in this case, participants in study 2 tended to be more stable overall because they had more established HIV infection. They were not in the high-risk group, and they were also not in the newly infected. So it's more an artifact of that, but it's what we expect. We would expect study 2 enrollment to be negatively associated with depression. Those other categories, probably if you look in the literature, they would generally also make sense in the direction of association. So again, always important to check, does this make sense with what I expect? Up there briefly. I know it's a lot of code. Any questions with that? No questions? All good, Johnny? All right, we'll keep going. Let's see how okay. Let's see if I can get through in the next 15 minutes. I think I'm sort of on track here. So we've covered lasso. Now we're going to get to random forest. And so with random forest, there's a few more hyperparameters we need to specify. We don't need to, we can use defaults, but just to show you what Python is picking, I put in some ranges. So max features, I have notes there. That means like, what are the number of features we're going to include in each tree? Again, as I mentioned, random forest takes a sample of features. Also the max depth, meaning what is the longest path in the tree we're going to allow. So if you think about if you have a garden at home and pruning your tree, this is kind of specifying, how do we want to grow the trees? And there's a trade-off in complexity, explainability, and just getting a good tree. And we also have a complexity parameter for how complex we want it to be. So I did this to show you that what happens if I run this model on the scaled data, which is commented out, or if I use the unscaled data. And I see I actually get really similar results, what I would expect. I would say in general, use the unscaled data for random forest because it's not going to help you to use the scaled data. If anything, if you think about what scaling does, it can make that boundary between the classes a little bit harder to distinguish. And so it could maybe hurt your accuracy a little bit, but in general, the results I would expect to be very similar. Now, another thing to point out, we actually didn't improve our accuracy with the random forest, right? So doing a more complex model doesn't mean it's always better. So that's something to note, because in this data set, it's not a huge data set by machine learning standards. It's under 2,000 participants. So fitting a very complex model might not even make sense. So, but what we should do, since we fit this model, is we should look at feature importance. And you can either look at it in a table or you can visualize it, which I'm a visual person. And again, I fit this to the scaled and the unscaled data. So again, what am I looking at here? What does feature importance mean? Well, there's this concept referred to as Gini importance. And what that means is, if you remember back to the tree I showed you on that slide, going down the tree, you want to pick features that best distinguish the classes, in this case being depressed or not. Which features best split the data as you go down the tree? And so that's what this is saying. We don't have regression coefficients, but we can say which features are actually going to be the best predictors in a sense of depression in this case. So let's look at the Gini importance. I mean, both plots are the same, which I wanted to make that point to you, scaled, unscaled data. Which variable really jumps out as a clear winner? Well, that one, emotional help, that is a Likert scale for emotional support from family and friends. So that's not surprisingly probably saying, you know, having emotional support from family and friends is a big indicator of what you're going to screen for with depression, right? It's not terribly surprising. If you look at other variables that jump out is age. Again, probably not terribly surprising. That one, it's got a long variable name, but drug use, NMJ, just means reporting a substance use in your lifetime other than marijuana. So again, probably not earth-shattering that is associated with depression. So again, this is really important. Look at some visualizations because it's just really hard to, otherwise, you know, how do you know how your model did it all? You want to make sure it makes sense. Yes, yeah.
Tend to say that which one is the feature important? Do you have the potential like 0.15?
Oh, I see what you're asking. Yeah, no, you don't. You just want it to be, it's kind of giving you an idea of how well it's differentiating. So, you know, like 0.3, it's not super high. It could be better. Like you want it to be higher. But as far as, is there one cutoff value, like a p-value? No, we don't have one value for that. It's just the higher, the better. But that's a really good question. Yeah. And any other questions? Yeah. Now, I mean, for me, when I fit a random forest, this is the most useful visualization. I want to know which features contributed the most. You might say to me, I still want to see a tree, right? Now, keep in mind, there's 100 trees that were fit by default, but you might say, I still want to see a tree, and you can. This is code if you want to see a tree. It's pretty messy, but it can kind of give you an idea. So if you look at the top, now keep in mind, again, this is one of many trees. So if you're going to look at trees, you probably want to look at, you know, multiple trees to kind of get an idea. But all you have to do in this line of code, oh, sorry, I went back too far, didn't I? I went ahead. All you have to do where I've got tree 1 and then I've got in bracket 0, you just change that to 1, then 2, and you can go up in the trees you visualize. But you can kind of see the pathway that, you know, again, that variable for support, that's the emotional support. And what that's saying, that if I start at the top, if I have a value on the Likert scale of less than or equal to, well, you can't get a 9.2. So if you're using this as a screening tool or referral tool, if someone has a value of 9 or less, and I think the scale only goes up to 10, that means that they go to the left for screening towards depression, but then you go down the tree to figure out, and you go all the way to the bottom. So this is just one example. I'm kind of rushing through this quickly, but can answer questions at the end about the trees. But this is your standard tree. Extreme gradient boosting. I just have the code for this one as well. This actually did a little bit worse too, which I'm not really that surprised, because again, you want larger data sets. But I wanted you to show you the code. If you have a big enough data set, extreme gradient boosting can certainly outperform random forest. I think in the literature, especially if you have Imbalanced data where the minority class is pretty low in proportion, extreme gradient boosting can outperform random forest. And just like we did for trees or random forest, we also want to look at feature importance. So the plot looks a little bit different. There's different visualizations, but again, extreme gradient boosting, you can see that emotional support and age came out on top. I'll just say one more slide before I end to say that it would have been beyond the scope of this workshop and quite honestly, my know-how, this would get into more Johnny's territory, that if you want to share these models with, say, other researchers, or you want to post them on the website, say for a clinician, where they can log in and enter somebody's values and see, should this patient be sent to referral or not, that's really gets into the power of Python. You want to be able to share your models, right? And so there's some of these Python libraries I listed that have features to create data pipelines to share your model algorithm on a website so other people can use it without sharing the data, keeping your data safe, but you're just sharing the model, the parameter values, so that they can actually plug it in. And so there's some libraries. And I will stop there. Hey, how about that? I'll give you a few minutes back. But any questions? Oh, yes, there's a survey. Thank you, Jay. You reminded me too. Please fill out the survey. So I'm going to sign off. Thank you all so much for coming. It's great to see you and have you on this. And we will have future workshops and seminars. So please be on the lookout. If you see an AIM-SWG heading, you'll see mentioned. And I know, our scientists from the AIM-SWG chips and other people will be presenting. So thank you so much.